Today we're going to go through solving systems of equations by substitution. We've already covered how to solve systems of equations by graphing, but there are times when we need a different way to find that all magic point where the two lines meet. For instance, what if your intersection point is not on a perfect grid? For instance, what if the coordinates were decimals or fractions, and it's hard to tell exactly what the coordinates are? Or the point is too high or too low to actually show on a graph with any reasonable effort. Well, fortunately for us, we have another way to solve systems of equations called substitution. In short, substitution requires that we solve or rearrange one equation to isolate a variable, then use that equation to substitute for that same variable in the other equation. Let's take a look. Just a reminder before we start on an actual problem that when we solve a system of equations, we're looking for an x value and a y value pair that fits both equations. In other words, points that make both equations true. We still have the three different ways that our systems can turn out. We can have a one solution system where our solution is a point. We can have a no solution system where our graph would be a set of parallel lines that never crosses, and infinitely many solutions where both equations turn out to be exactly the same line. In our first system, we're going to solve y equals 3x combined with 2x plus y equals 10. If you notice, the first equation is already solved for y, which means y is isolated or by itself. So we're going to take what y is equal to, the 3x, and use that to replace the y in the second equation. So if we take our second equation, the first equation, y equals 3x, means that y and 3x are one and the same. They're interchangeable. So in the second equation, we're going to take that y and substitute the 3x in its place. Now, because of our substitution, notice that we have an equation with only one variable, and we can use that equation to solve for x. Combining like terms gives us 5x equals 10, and dividing both sides by our coefficient of 5 gives us x equals 2. X equals 2 gives us the x value or x coordinate to our solution. Then there's a second part to solving using substitution. We actually do two separate substitutions. Now that I know that x is 2, I can come back up and choose one of my two original equations. You can choose either one. It's not going to matter. If you've done all your calculations correctly, they should both give you the same value for y. Since the first equation looks a little easier to use, I'm going to choose that one. So if x is 2 and y is equal to 3x, I can substitute again and change y equals 3x into y equals 3 times 2. That gives me a value of y equals 6, and now I have a y value and an x value for my solution. And since the solution to a system is a point, I can write our solution as the point 2, 6. Let's do that again. Here I have another system of equations, both with x's and y's for our variables. But notice this time, neither equation has a variable that's isolated. So I need to take the time to do just that. Sometimes you'll have one variable that's easier to isolate than another. And it seems to me that since this y only has a coefficient of 1, this y is going to be very easy to isolate simply by subtracting the 3x to the other side. So if I take 3x plus y equals 7 and I subtract 3x from both sides, on one side it's going to cancel, on the other side those terms can't combine since they're not like terms. I get y equals 7 minus 3x. Now that I know what y is equal to, or have some kind of value, some kind of equation or expression that y is equal to, I can come back to the other equation that I haven't used yet. It's important to note that you can't substitute back into the equation that you just rearranged. That creates all kinds of havoc. If you rearrange one equation, substitute it into the equation you did not rearrange. So since y is the variable that's isolated, I'm going to substitute in for y. I'm going to remove y from my original equation and replace it with 7 minus 3x. Then we can use our mad equation solving skills to solve this equation for x. First doing the distribution, combining like terms, subtracting our constant from both sides, and dividing both sides by our coefficient. I end up with x equals 3. Now that I've solved for x, we're not quite done, because in a point I need both an x value and a y value. So I need to come back. I can use any of the equations that you see on the screen to help me find a value for y. I'm going to choose the equation that I rearranged so that y was isolated. If y equals 7 minus 3x and x is 3, I can replace x with 3 and solve. Using order of operations, I get 7 minus 9, which means that y is equal to negative 2. Now I have my solution. The solution is the point 3, negative 2. Be really cautious that you're putting the x value first and the y value second, just like in any point in a coordinate system. Let's take a look at another. Do we have one variable that's going to be easier to isolate than the others? You bet, this x in the first equation. Sometimes you won't have one that's super simple like that. You'll have to rearrange the whole thing, but that's okay. We know how to do that. So if I have x minus 6y equals 18 and I add 6y to both sides, I get x is equal to 18 plus 6y. Then I go back to the equation that I haven't rearranged, and since x is the variable isolated, I'm going to use it to replace x in my second equation. Removing x from this equation and replacing it with 18 plus 6y is what substitution's all about. Now I can distribute, combine like terms, and look what happens. Our variables are completely gone. We have nothing left to solve for, but look at what's left over. Negative 54 equals negative 54 is a true equality statement. This is an instance where we have infinitely many solutions. If you rearranged both of these equations, you would get exactly the same equation in return. There's two cases where your variables are going to disappear. In the first case, like this one, my variables cancel and I get a true equality statement. That's a situation where I have infinitely many solutions. If, on the other hand, your variables canceled and you were left with a situation where you had an untrue equality statement, like 7 equals 10 or 0 equals 15, that would be a no solution system. So be cautious. If all your variables are gone, you either have infinitely many solutions or no solutions, depending on whether you have a true statement or a false statement. One more. Here we have two equations that are already isolated for y, right? They're already rearranged so that y is isolated. This is no different than any other system. I'm going to take that first equation and I'm still going to replace y in the second equation. If I replace y with 3x plus 6, I have an equation that I can solve for x. Subtracting 2x from both sides leaves me with 1x on the left. Subtracting 6 from both sides leaves me with negative 10 on the right. X equals negative 10, and we're halfway done. Substituting x equals negative 10, substituting negative 10 in for x into one or the other of our two equations will give us our y value. Replacing x with negative 10 and using order of operations, we get y is equal to negative 24. So our solution, don't forget to write your solution as a point, is the point negative 10, negative 24, always putting the x coordinate first and the y coordinate second. Just to solidify what we did today, we rearranged one equation so that I had a variable by itself or isolated. Then we substituted what that isolated variable equaled into the other equation, the one that I didn't rearrange, to solve for the remaining variable. Then I did one more substitution piece where we substituted that number into the different equation, the equation that you didn't rearrange, to solve for the second variable. Oh, I guess this one it didn't matter which equation you substitute it back into, but you were able to solve for the second variable. Okay, I think that's enough for today. I hope you have a fantastic rest of your day, and I'll see you next time.